All right, everyone. We are now in week four, and this weekend, I'd like you to watch this video for you to um, complete integral calculus. We now have the last portion, which is the area under a velocity time graph. Okay, let's start with this particular situation. I'd like you to pause this video and read the situation first before you continue. Having read the situation here, you might find this graph quite familiar because a velocity time graph would simply look like this. So if you're going to analyze, the person's velocity is actually having a constant rate of change, which in this case is negative because it's sloping downwards. Hence, we can conclude that the person is slowing down as time passes by. So if we try to understand it, the speed of the person, since the speed of the person is decreasing, that means the distance, the displacement he covers every second also changes. So the distance he covers after 1 second would definitely be different that after another second, and so on and so forth. So at each second, the displacement is different. Okay, so here the displacement is longer at 0 second because the speed is at 10 meters per second. And at this particular time, t equal to 4, the displacement, we can expect that the distance covered would be lesser. Okay? So if you try to look into, or if you try to solve for the change in displacement, the net change. So the clue here is the word net change. So if you try to put it into another subject, when you talk about net, say net salary is equal to gross minus expenses, and that is your net salary. In other words, if you talk about net change in displacement, we are talking about how your displacement changes. And for us to know how or how much, that would be the current minus where we start with or the previous. So in this case, to find the change in displacement, that will just be the integral of the velocity function from A to B, given that A is the starting, that is where we start with, and B is where we wanted to focus with, or that's the present, in other words. Now, you might be wondering, why are we trying to get the integral? Again, based on our previous discussion, to get the displacement, we are looking into the position time graph, the position of the object at a given time. Therefore, to get that particular function, we need to get the integral of the velocity function. Okay? So in other words, this will just be more or less the same to what we did in the other activities we've had, like the areas under the curve. So the thing would be familiar to you. However, if the question now is the total change in displacement, when you talk about total change, in other words, we're not just looking into the current minus the previous. We're looking into how the displacement changes at each time. So we wanted to add all of them, each of the change in each specific time. So the change in displacement in this case somewhat would become negative because this is actually going down. But then the total change should be positive. All right. So for that to happen, all we have to do is just to put in an absolute value symbol. All right. So to review everything, if you talk about net change, it's the current minus the previous. That's why this is being used. And oftentimes, especially if the slope is negative, the result would also be negative. Okay. However, especially again, why is it negative? It's because we expect at this point the displacement covered would now be lesser compared to the previous one. So if you listen to the first part of the video, this is the velocity is decreasing. All right, therefore the later part would be lesser compared to the earlier part. Therefore, the change in displacement, the net change would be negative. However, the total change, we're talking into the individual changes. Therefore, it should be something like positive. Okay, so the total change should be positive. For us to ensure its positivity, we have to put in an absolute value symbol. Okay, we could also extend this concept if we have net change in velocity, and of course we have net total change in velocity. Okay, so if it's net change in velocity, we just have to integrate the acceleration function. Let's try to see some examples. Let's try to have this. Pause this video and read the example. So if you have read the situation here, you can find out that we're given the function of the temperature capital T with respect to time, small letter t. For you not to be confused, you can use other variables other than both being t's because that might be confusing. So all you have to do here, if you try to look at it in order to find letter A, is first you need to write this in this particular form so it's easy to understand. So here, t prime of t is simply the derivative of t, the rate of change of t with respect, the rate of change of temperature. Let's make it clear with respect to time. So if you wanted to find the temperature function, you just have to find its integral. Thus, for letter A, if we wanted to find the net change, this is actually net change because we wanted to compare from a temperature of 0 to a temperature of 8 degrees Celsius. Since we're looking for the net change, it will just be from 0 to 8. No need to put an absolute value symbol. Okay? And thus, we get a value of negative 21.33 degrees Celsius. This is not the net change. But then if we talk about the total change in temperature over that period, then that's the time we put a parenthesis. We put an absolute value symbol. Okay? Now, the moment you have written this, you can use your GDC and compute, and thus we get an answer of 76.76 degrees Celsius. So that's the difference. You just have to look into the clue. Is it a net change or is it the total change? Sometimes net and total is not given. You have to analyze it yourself. Just like in the situation, in the first one, you're not told it's the net change. But take note, you're talking about the change from 0 to 8. So it's just simply a net change. Let's have another example. Once again, pause this video and read the situation. Alright, I will leave letter A for you to do since it's sketching the curve and you can do this using your calculator. Let me start with letter B. So for letter B, so we are to find the net change in the volume of water in a 24-hour period. So we can actually just simply find it. It's a net change, that's 0 from 24. So we get this amount, negative 120 cubic meters. Now for letter C, we are trying to find the total amount. So just add absolute value symbol, and that gives us this particular value. Now for letter D, we are going to determine a formula for the volume of water in the reservoir at time t, given that the volume. So in this case, we are now going to find a specific function. So whenever you're given values of time and velocity, or you're given the values of the variables or the quantities in focus, then you are going to find a specific function already. Remember, sometimes your function is having, or when you integrate, you have plus c. That's not specific. So if you wanted to make it specific, you need to solve for the c. And that is what we are looking for here. For B and C, you can use your calculators to compute. But for letter D, you need to do it manually because we are going to integrate it, meaning without boundaries. We are going to integrate it in order to come up with a specific function to address letter D. So we're going to integrate this using our techniques of integration. All right. Now, at this case, I will focus on the sign of this particular angle because negative 5 is a constant. Therefore, when you integrate it, it will just be 5t. So I will focus on this. So the technique that we have for this is actually to use reverse chain rule. So this will be our u. And if you try to integrate that, you will get d over dt equal to pi over 12. And then dt will just be equal to this. So we can now substitute this one. All right. And then, by the way, pause this video. Whenever you're confused, pause the video. And then we will be able to get this particular integration here and simplifying it. Thus, we already get this particular function. But this is still a general because we have a plus c. So we need to solve for the c. Okay, so to solve for the C, we need to have specific values of volume and time. Here it's given that volume is V sub 0, that's the initial volume, at midnight. So since it's a 24-hour period, we expect that midnight is the starting point by which we count it as 0. Okay? At 1 a.m., it's 1 hour. At 2 a.m., that's 2 hours. So at midnight, it's t equal to 0. Therefore, that is what I'm saying, no? At midnight, t is equal to 0, and we're given that the initial velocity is v sub 0. So we don't know the initial velocity, we're just given that it's represented by v sub 0. So this is now our function. So we now have, so we substitute, no? We substitute t equal to 0 in our derived function a while ago. So our v is v sub 0 as given. And when you do substitute, then some of which will be cancelled because t is equal to 0. Thus, we will be given this. In other words, your v sub 0, if you try to algebraically manipulate it, your v sub 0 minus this particular constant, this will just be a constant. If you try to look at it, is just equal to c. So c then is equal to v sub 0 plus 22.15. Again, pause this video if you're quite confused. So we can now put this in back to our original function. Thus, we have this. All right. Now, for number 2, find the value of b of the volume when t is equal to 24, and we are going to confirm if the answer we got a while ago, which is negative 120, is the same. Okay. So this is the net. So the net meaning we go back to letter b. So it must be this answer should be the same with letter B. So using the new function we derived, let's try to find out if the answer would be the same. So here we're given that t is equal to 24. Okay, take note that it's from 0 to 24, right? Because it's from midnight and after a 24-hour period. So t is equal to 24. If we are going to substitute t there, we will get this. And if you are going to simplify it, the volume after a 24-hour period will just be simplified as negative 120 plus v sub 0. So to find the net change from midnight and after a 24-hour period, we have to subtract v of 24, that with the initial, which is v sub 0, which we do not know. So v, the volume after a 24-hour period, given is derived as negative 120 plus v sub 0, so this one, minus, we have here the initial volume, v sub 0. So if you simplify this, therefore the net change really is negative 120 meter cube. Therefore, it confirms that what we did in letter B is the same as the answer in letter D. Thus, this tells us that when we talk about net change, we can just use the method that we used a while ago. If you wanted to have it longer, then you can use this one. Okay, so somewhat this is an explanation or a proof or a confirmation that what we're doing previously in B and C really is correct.